So, you can hear us okay, Tobias?
Yes.
Cool. We'll turn you up in a minute. But Tobias is an engineer at Google Sydney, but has a very strong connection with New Zealand, amongst other things, a graduate from Canterbury, and also has been quite involved with the programming competitions, not only winning a prize in one, but also then coming back to help tutor a lot with the camps and so on in Auckland. So really appreciate all that, but I've asked Tobias to talk a little bit about being a software engineer at Google and so on. I'm going to hand over to you, and I've got some slides here that I'm going to try and keep in sync.
Excellent, thank you very much, Tim. Sydney, everyone. I'm Tobias. I'm a software engineer at Google Australia here in Sydney. I lived in Christchurch for 4 years before that, and originally I'm from Germany, so I've come around a bit. First of all, can you go to slide 2, please? Can you give me a quick show of hands? Who of you uses Google Drive? Oh wow, that's more than half, I think. That's quite a few. For those of you who don't know, it's an online word processing and spreadsheet and so on software which runs in your browser, but also has local native installations for Windows and macOS, and also on smartphones running Android or also on iPhones, and where you can also upload arbitrary files. So I'm a software engineer. I work on the Google Drive application for Android, and as you can already see, Google Drive for Android is only a small part of that, and of Google Drive, and Google Drive again is only of the over 600 products that Google is launching and releasing and working on. So it's really a big organization these days, and with this size come complexities, and that's why the field of software engineering has had to mature quite a bit over the last 20 years. Can you go to slide 3, please? So software engineering really is only one part of computer science, and that's the part that I want to talk the most about today, because I'm a software engineer, that's my job. And software engineering is an engineering discipline. We are building things. We're not building bridges, we're not building cars, but we're building software. And software engineering is the art of developing a systematic approach to developing that software. A surprisingly large part of software engineering is the challenge to keep things scalable. Scalable means you want to be able to process large amounts of data, you want to be able to serve more users, you want to be able to run faster, and so on. And the picture that I'm showing here is that of a Google data center. It's basically a very big room filled with tens of thousands of computers, very tightly packed and engineered very specifically to fit into as small space as possible and run with as little human intervention as possible. And those are the sort of computers that when you access Gmail or you search on Google Web Search or you access Google Maps and so on, they will run the software that powers that will run in a data center like that. And similarly, if you access Facebook or Yahoo Mail or any other web services, chances are the software will be running in a big room full of machines like that, and probably not just on one machine, but across multiple different machines. And architecting the software in such a way that it can benefit from running across, for example, 10,000 computers at the same time is a major challenge in software engineering. And can I have the slide number 4, please? Okay. So, as I said, scalability is the main thing we want to optimize for in software engineering. And some of the constraints we run into are physical. For example, the speed of light is way too slow. We would like it to be much faster. Everyone thinks the speed of light would be fast, but when you think about the fact that the circumference of the Earth is 40,000 kilometers, then it takes light more than 100 milliseconds just to go once around the Earth. So if you're accessing your Gmail, you're sending a keystroke or something, you send some request to the server. It takes, if the server is on the other it takes at least 100 milliseconds to get a response. And for many applications, that is too slow, much too slow. And for that reason, Google has not just one data center, we have data centers all across the world, so that every user service, if you're physically in New Zealand at the time you're using the service, you will be connected to a data center that's physically, geographically close to New Zealand to ensure a fast response time. Similarly, on modern microprocessors, the clock speed is in the order of 3 gigahertz. So in the time between 2 clock cycles, processor to multiply two 20-digit numbers, light will only travel about 10 centimeters. And so a processor is maybe 2 centimeters across, but the paths, the communication paths on the processor are not direct. And on modern processors, it actually takes multiple clock cycles for the signal of the clock to travel from one end of the computer processing core to the other end. So we're running into all these physical limits there. Other constraints that we deal with are that of complexity theory in a more information theory set. For example, if I want to sort two numbers, I just have two numbers and I want to put them in the right order so that the smaller number comes first and then the larger number. That's very easy. I can make a single comparison and then swap the two numbers if they're in the wrong order. And if I have three numbers, then I need two comparisons and so on. But if I have a lot more numbers to sort, then if I only compare adjacent numbers in the original order and swap them if necessary, then the complexity of this approach will grow predictably with the size of the input. So if I have twice as many numbers to sort, then it will take 4 times as long. And then you quickly run into issues where even a computer is not fast enough. And then a field of computer science is that of algorithms, of developing approaches where you can do that more scalable and more efficiently. And there are ways to sort numbers that grow almost linearly. So where if you sort twice as many numbers, it'll only take a little bit more than twice as long. And so in software engineering, we're also concerned with finding a really efficient way of doing the same, solving the same problem according to the same specification. As you scale and you have a more complex system, a larger computer program, more engineers, more users, more data, the number of defects that we have also grows. And there's no software in the world that is completely free of defects or bugs, as we call them. For example, I'm sure Microsoft Windows will have hundreds of thousands of defects. The problem is we don't know which ones. and even if we do know, then in many cases finding the root cause of the defect and fixing the defect is so difficult that it's prohibitive to fix any serious portion of them. So managing defects so they stay within an acceptable limit is a very difficult problem. And if I transmit data over the internet or something, then I might not get the same data at the end of what I was sending. So famously, there's this joke, what do you get when you sort 10 trillion integers? Well, you get an almost sorted set of 10 trillion integers, because somewhere along the way, maybe there was a cosmic ray that hit your processor and some logic behaved faulty or something, and you just don't actually get a sorted output. And if you run the same sorting algorithm again, you will get a slightly different, almost sorted set of 10 trillion integers, and so on. So as we scale, we run into all kinds of obscure limitations, and there are many ways to fix that. For example, in airplanes, in an Airbus airplane, all the computers will have 2 or 3 identical copies that run in parallel, and if 2 copies agree and the 3rd copy of the computer has a different result, then they will conclude that the third copy is faulty and will be overridden by the other two computers. And specifically the defects that arise in software, I'm going to discuss on the next slide, on slide that.
Slide 5.
Yeah. So software engineering as a discipline has developed strategies to cope with the defects that naturally arise in software, and some of them are controversial. I hear you guys have heard about waterfall and agile programming and so on. Basically, everyone agrees that waterfall is rubbish, but not everyone agrees that agile programming is the saving grace. And if you ask different people, they also have different opinions on what exactly the term agile programming means. I personally think it's a terrible term. It's like calling your church the church of good people, and then if you're not a member of the church, then you're not a good person, clearly. Like, it's a biased name already, and if you're not following agile programming, you're not agile, you're slow or whatever, and that doesn't really hold. So there's a lot of controversial things like that, but there is a set of practices that are really universally adopted across the industry, where everyone agrees that they improve the quality of the code that we write. So first of all, a programming language in itself is much more rigorous than a natural language. If I make a grammatical mistake, I've probably already made 10 in this talk, then you will just be able to understand me anyway and won't even raise the issue with me. But if I make any grammatical mistake in a computer program, then the computer will completely refuse to execute it at all. Because the semantics are very precisely defined. And beyond the restrictions that the computer imposes, because the programming language is defined in such a very strict way, there are additional idioms and conventions that we impose in our engineering practices to make sure the way software is written is very standardized. So for example, in natural language you have things like poems and so on. In engineering we wouldn't really have that. That's like, poems are the classical non-traditional way of writing speech. And in programming we follow very strict guidelines of how exactly something should be written, so that's very quick for someone else to understand, and so we can write isolated components that are reusable and that we can test independently again to achieve that scaling. The next practice that's really universally adopted is that of code review. When I write every single line of code that I write, I cannot just check into the version control system and have it go live on the Google web servers. Every piece of code I write will be reviewed by at least one other software engineer, and they will try and find defects in what I wrote. They will comment on the style of what I wrote, how I wrote things, whether I wrote enough automated tests, whether my documentation is appropriate, whether my choice of naming for variables is clear, and so on. And typically, any code that I write will go through 2 to 5 rounds of iterations before I can actually get approval from my fellow engineer to submit it into the version control. The next step is automated and manual tests. So testing that the software actually performs according to specification. For example, if I have some button in my application, every time I click the button, I want some dialog to pop up. Now, I could just write that into a document that some human reads, and then theoretically, to be sure that my application still performs in this way, some human would have to click that button and verify whether the dialog shows up. Of course, that's not really very scalable. If you have millions of changes going in, then you don't want to have to click that button a million times. And that's why we write software to test our software. For example, some software that will then click that button or simulate a click on that button and check whether the program behaves as appropriate. And in many companies, the testing organization is actually larger than the organization that writes the original code. And the Microsoft Windows testing organization is famously huge, has thousands of people, maybe even tens of thousands of people working on just testing Microsoft Windows and finding bugs in it. And when we do find bugs, we put them into an issue tracking system, which maintains a list of all the issues that we have found and what the status is of each issue, whether a particular person is assigned to work on it, whether it was fixed on a particular day by a particular change, and in what versions of the software occurs, and things like that. So we manage the issues with that. All right, that was software engineering so far. I'm quickly going to go through other roles that exist at Google. So Google is a technical company, so we have a lot of technical roles, but about 50% of our staff are actually only in R&D. The other 50% are salespeople, marketing, facilities which look after buildings, the kitchen staff who cook our meals, physical security, all kinds of other people, and legal, lawyers, and so on. Yeah, but even in engineering, it's really diverse. There are a lot of different roles with lots of different skill sets. I've already talked about software engineers, which are people like me who write the code, and I've talked about test engineers and software engineering tests, which is the green circle, who are the people who test the code. But hardware and network operations, who build the data centers that our computers run in, and who build the network and monitor the network, and site reliability engineers have the task of ensuring that once an application is deployed, it continues to run. So for example, if Gmail doesn't work anymore one day, you can bet that there are at least 5 site reliability engineers who carry pagers, who will get woken up in the middle of the night, who will have a service level agreement of logging into the system within 5 minutes and finding out what the issue is. And developer relations, for example, are people who... Google has a bunch of APIs, interfaces where other programmers can interface with Google systems, and developer relations advocate use of those systems and talk to other software engineers outside of Google on how to use our systems, and so on and so on. So there are lots of different roles at Google alone, and of course even more so once you include other companies. I'm not quite clear how long I've been talking, so let me know whether I should stop here or whether I should continue.
Yeah, we've probably got another few minutes if you've got it.
Okay.
Yeah.
All right. So can we go to slide number 7 then?
Okay.
So the following points are things that you are all already aware of and that you've probably heard a million times already from other people, but I thought I would give some more examples of why I think these specific points are really true about software engineering and computer science in general. And I've identified 4 properties which I think really make software engineering different from any other discipline. The first one is that how large an impact it has on very originally disconnected other fields. Basically, you do not get away without knowing computer science anymore today, regardless of what you do. There were tons of Nobel Prize winners in biology or whatever successful linguists who didn't know anything about computer science and who were still very successful 50 years ago. Because back then all the other biologists and linguists didn't know anything about computer science either. But today that's no longer the case. And when you have a field where there are some people who do use computer science and others do not, you can prepare for that field being disrupted. It hasn't happened to all fields yet, but it's happening to more and more fields. So I actually studied bioinformatics, and in 1990, one of the hit things in biology was the Human Genome Project, aimed to sequence the entire human genome. A fun fact, the human genome is actually a digital core. It's made up of 3 billion base pairs. Each base pair can have one of 4 different states. So it's basically a base 4 number system, versus computers deal with bits, which are a base 2 number system. A bit can have one of 2 different states. And so the entire amount of data stored in the human genome is about 750 megabytes. It's a little more than fits on a CD. It's less than 0.1% of the capacity that your hard drive can store. And so the Human Genome Project had this ambitious goal of sequencing the human genome, and they had set themselves a milestone of 30 years to do it. And it was a huge international collaboration between biologists, researchers at various universities. Until in the late 90s, a private company came on board who had only a few biologists and a bunch of computers, and they completely revolutionized the way the Human Genome Project worked. They used a different technology to sequence very short sequences of the human genome, only a couple hundred base pairs at a time. But if you know that these 300 bases appear in the human genome in sequence, and these other 300 bases appear in sequence, and you have millions and millions of these little bits of information, then basically it's a computer science problem to work out from these many bits of information what the complete sequence of the human genome is. And that's exactly what they did, and they finished much faster, and then they finally published their result. I can't remember if they published in Nature or in Science. Then the public, non-private Human Genome Project was more or less forced to publish their results to date in the other journal, but they weren't as far yet as the private effort had come that started 20 years later. Similarly, machine translation. Machine translation is not quite as advanced yet. So if you translate a Chinese website into English, using Google Translate, for example, then you will obviously see that this English text was not written by a native speaker, but it will be good enough that you understand the content. And it's now language barriers in a major way today. Another thing is the movie tree. Movie industry used to be about hiring good actors and wrecking cars in a spectacular fashion and making explosions and all of that. And today, more and more of the movies are done in post-processing after the actual video is shot on the computer, and many times movies are made entirely inside a computer. So really, there's no area where computer science doesn't at least help, and many areas that have traditionally been considered very different from computer science, such as biology or shipbuilding or movies or linguistics, are now being disrupted by the advance of computer science. And it's also a leveling ground internationally, because the know-how, the technical know-how is the main limiting factor. It allows people in other countries to compete more effectively with the established Western industrial nations. And yeah, so it's a disruptive force in both directions, and not all countries will necessarily benefit from this change in the worldwide. And I would say that New Zealand and Australia and Germany are all among the criminally privileged countries and have to be really careful to make sure that their young future generations are appropriately educated to be able to compete in this changed environment. Can we go to slide number 8, please?
Okay.
Another thing is, because computer science has grown so recently, it's caught many people by surprise. Suddenly there's this really important field, and they didn't really see it coming, and they thought it was a fad or something, and demand or supply of software engineers is slowly catching up with demand, but we're not anywhere near that. And as a result, I feel really pampered. Like, I get free food, I have a great office environment with games and so on. If I lie down for a nap in the middle of the day, no one says anything. I get a great salary, and that's not just at Google, that's at all companies. If I quit my job tomorrow, I will have zero concerns about whether I'll find another job the next day. And I don't know if that's true to this extent in many other industries. I think there's never been a better time to be a software engineer than today. I'm guessing that in the next 10, 20 years, this will somewhat go down because there will be more and more graduates competing for the same jobs. So it's not necessarily going to get better, but it is pretty awesome at the moment. And the last law, number 9, other facts about computer science and software engineering is, first of all, your imagination is the limit. I was talking about scalability before and how really we are working, a big part of engineering is working, tearing down boundaries to how far we can scale. And famously, for example, at Facebook, they have more than 1 million users for every engineer that they employ. And I don't think many car companies can say that they have more than 1 million customers per employee. And I don't think many schools can say that, and I don't think any other industry, right? It's only in software engineering that you have this large, massive potential scale of impact that you can have on one person. And the last good thing about software engineering that is one of my personal favorites is that it's developed so recently that all the little countries have had no time to come up with their own little pet standards of how software engineering should work. It's quite amazing to think. You would think that the human body works about the same way everywhere in the world, but if you study medicine, it's really, really hard to get your degree recognized in a different country and move internationally. Some countries, like Western countries as a group, have more or less agreed on a standard, but even within them, it can be difficult to move internationally. So I grew up in Germany, I moved to New Zealand, and then I moved to Australia. It was absolutely no problem for me to adapt to the work environment in each of those countries and find work. And that's a great opportunity, but it's also a challenge because it means that people educated in India or in Africa or in Asia can also compete and move to New Zealand and whatnot. So it is a challenge, local workforce, and it is equalized to some extent where barriers between countries are broken down. And yeah, it's really important to look after the education of our next generation, sure that we can continue and be as easy for an industrial nation to suppress a third world country anymore as it used to be if they do not compete on the education front. All right, now I think we have some time for questions and hopefully answers.
Thanks, Tobias, that's tremendous. So, yeah, questions. If Tobias can't hear them, I'll just relay them from up front. The microphone's here if anyone would like to ask him something.
Yeah, hi. I have a question about testing. I understand the test methodologies and that, but don't companies like Google and maybe other companies increasingly go out with alpha and beta versions to their clients and get effectively them to test before they do the big release? Like you guys may release to only like 10% or something of your population of users?
Hey, do you want me to relay that?
I heard it was about testing, but not much more.
Oh, okay, yeah. So I guess the question is, some of the testing is done by alpha and beta releases, and Google is, I guess, famous for having beta releases that are the kind of testing. And also, do you do testing by like releasing things to 10% of your users to see if they work? So answering the last bit first, we absolutely roll out gradually where possible. So if Google Web Search makes any sort of change, that change will first go live to only like 0.1% of all users, and then observe the effects. And if everything goes well, they will gradually roll out to more users over the next couple of months. And that's not possible in all cases. For example, for our Android app that I work on, there's no technical way for us to roll out just a fraction of the users. The only thing we can rely on is that not everyone will update the application at the same time. The beta thing is not really so much for testing, I don't think. So personally, I don't know what the official company position on this is or anything like that, but I feel that Google has used the word beta mostly as a way of appearing humble and saying and not claiming that their software is any better than it is. But I mean, Gmail wasn't beta until like a year ago or something. It's been in beta for, I don't know, 8 years or whatever. And all that time it was actually a perfectly good software.
and no worse than other softwares that do not carry the label beta. So that's just a name. So software testing has there are many different points at which we try to find defects. And we try to find it as early as possible, because the earlier you find a defect, the easier it is to fix. If you only find the defect after the product has shipped to your customers, it's going to cost you at least 1,000 times as much as if you find it during code review. And each of these steps will find a certain percentage of the errors. It's a statistical exercise, basically. And everyone will have to rely on, to some extent, on the users testing the software, in the sense that if you've only used the software within your company, even maybe 50 people, maybe 30,000 people as a company, you're still not going to have found all of the bugs. And once you release it to 5 billion people, then yeah, you'll have thousands of new defects that you have never encountered before that creep up. But I think the fraction of problems that get fixed after the product is launched is only a tiny fraction of the number of problems that we fix. The most problems I find immediately after I write the code. So I write a line of code, and then I think, oh, no, wait, this doesn't work. And then I change it, and no one ever sees that code, and then it's fixed. And then the next one is during code review. My code reviewer will carefully think through what my code does, and then they will hopefully find problems. And then the next step is unit tests, automated tests. I have other software that tests my software and make sure it's correct. Then we have manual testers who actually use the application and will tell me if they find anything that misbehaves. Then we have dog food, which means, so Google has this policy, eat your own dog food, that any software that we want to ship to our users, we should be willing to use ourselves as well. So before the software actually goes live to everyone else, we will first use it inside the company. And then we get feedback from the 30,000 Googlers or however many use it. And then after that, we can roll out to our customers.
Great, thanks, that was a good answer.
It'd be fantastic if you could speak to our students. Would you be willing for us to contact you, and maybe they ask you questions?
You want my contact details so you can pass them on to your students?
I'll translate that. Would you be prepared to talk to the students like this, I guess?
Yeah.
Is it? Yeah.
Yeah, sure, I can do that.
Fantastic, thank you.
Cool.
I'm even willing for students to contact me directly, but maybe not all of them.
Yeah. Cool. Just time for maybe one more question. If there's, yeah, sure.
If you've got software that tests your software, but the software that you're writing is new, how does your test software know what to test?
If you've got software that tests your software, but the software you're writing is new, how does the software know what to test?
Well, we write the software that tests the software at the same as writing the software as a test. So basically, every time I develop some new feature, for example, let me think of something. Like, for example, recently I added the feature to the Google Drive app that you can send the link to a document and copy it to the clipboard. So that I can then paste it into an email or into an SMS message or however you want to share that link. And at the same time as I wrote that feature, in the exact same change list, I wrote software that used this component of the application or test and verified that after it used that function, that the linked document did indeed end up in the clipboard and that I could access it.
Yeah. Cool. Okay, hey, Tobias, thank you so much. I think that was really helpful. Yeah. So let's thank Tobias. Cool. Okay, I'm going to hang up on you and switch to the next session. Thanks very much.